Last chapter, chapter 9, sequences, induction, and the binomial theorem. So we are actually not going to get to induction or the binomial theorem. So we are going to start with sequences by first writing the first several terms of a sequence. And this is what we actually started doing last time before the exam. Then we're not going to talk about a recursive formula because we don't need that right now. But we are going to talk about summation notation. So we're going to use summation notation. And then find the sum of a sequence. So what happens when we start adding up the numbers in our sequential list? So here's a definition that we need. A sequence is a function whose domain is the set of positive integers. So this is a way of thinking about sequences. So the domain of a sequence is the counting numbers 1, 2, 3, and so on. So let's look at a particular sequence. So this sequence can either be written as A of sub n equals 1 over n, or it can be written in function notation with the understanding that n is 1, then 2, then 3, and so on, and is not continuous. But compare this to the continuous function f of x is 1 over x, and see that at the places where the values of x are the positive integers, that those dots that represent the sequence fall exactly on this graph. So our first objective is going to be to just write the first several terms of a sequence. So we looked at these first two in class, and we talked about that you let n equal 1, and then 2, and then 3, and then 4, and then 5, and then so on. So we had that the b sub n's, when n was 1, we got 3 halves. When n was 2, we got 5 fourths. When n was 3, we got 7 sixths. And then 9 eighths, and I can see that the denominators are going 2, 4, 6, 8, so the next denominator has to be 10. And on the numerators are going 3, 5, 7, 9. I can see that the next numerator is 11. So we write these with commas in between them, and then say comma dot dot dot, which is called an ellipsis, that says and so on in the same way. So we can see, I want to look at this for a minute, this 2n plus 1. And think about what kind of numbers you end up with. Well, every even number can be written as 2n, right? If you think about any even number, it has 2 as a factor. So that means it can be written as 2 times something. So then if you write the number 2n plus 1, it's the number 1 bigger than an even number. Well, that means it has to be an odd number. So the sequence 2n plus 1 is actually just the sequence of odd numbers, if you think about it, starting with 3. So you'd have 3, 5, 7, 9, 11, and so on, as n equals 1, 2, 3, 4, and 5. So think about this. This comes up frequently, that 2n, the sequence 2n, is even numbers, and 2n plus 1 is odd numbers. And then remember that we noticed that if I have negative 1 to the n minus 1, let's look at a few of the terms in that sequence. When n was 1, I got negative 1 to the 0, which is 1. So then I had 1 over 1, which is 1. So these are the d sub n's. So then when n is 2, the power on the negative 1 is 1, and so that gives us a negative value, and it's 2 in the numerator over 3 in the denominator, comma. Then when n is 3, I get an even power on the -1, so it's positive. And then I'm going to have 3 over 5. And then when n is 4, now the power on the -1 is odd, so I get a negative number, 4 over 7. And then you can see the pattern again. 1, 2, 3, 4, 5 are numerators. 1, 3, 5, 7, 9 are the denominators. And the sign alternates. That's what the -1 to the power does. So notice that 2n minus 1 also gives you odd numbers, because right before each even number is an odd number, and right after each even number is an odd number. So now let's go the other way, because I always pretty simple. You just plug numbers in and there you go. Well, now we have a pattern and it says the pattern continues, and we've got to try and figure out how to write the nth term of the sequence suggested by this pattern. Well, we just talked about even numbers, so we can see that this is going to be 2n. But there's going to have to be a -1 to a power to get the sign to alternate. So let's see, this is n equals 1, 2, 3, 4, 5. So if I do -1 to the n, the sign's going to be wrong. But if I do -1 to the n plus 1, then do you see that that makes the sign alternate in the correct way for this particular sequence? Okay, then number 27, I have 1, 2, 3, 4. So what I do is I write the n's nearby. So I can say, oh, these numerators are n. They are n. Oh, and the denominators are 1 bigger. So n over n plus 1. So other things to look for are powers, like n squared, n plus something, n minus something. If you see that you're going up by 2's, then that's what the 2n does. So 2n plus 3, for instance, when n is 1, you're going to get 5. Then when n is 2, you're going to get 7. When n is 3, you're going to get 9. So do you see how you're going up by 2 each time? That's what this 2 multiplying the n does. It says this is the size of the jumps between the numbers. Okay, so I'm seeing 2, 4, 8, 16. So let me write n equals 1, 2, 3, 4. So the numbers are doubling. So that should make you start thinking about exponentials, because exponentials double. So if I have 2 to the n, that looks like that's giving me the numerators. And then in the denominator, I'm multiplying by 3, then I'm multiplying by 3, then I'm multiplying by 3. So that looks like 3 to the n. And they're all positive. So that looks like that will give me each term of that sequence. So practice a lot of those. It takes a while to get good at recognizing them. Okay, so now we need some definitions about factorials, because we will be using them more later. So there's the factorial symbol is this exclamation point, and is defined that 0 factorial is 1. So we don't have time to go into the details of why that has to be so, but 0 factorial is 1 and 1 factorial is 1. Then for bigger numbers like 7 factorial, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. Well, fortunately, your calculator has a factorial button on it somewhere. We'll work on finding them together in class. And then I do want you to notice that if I do 7 factorial, and then I look at 6 factorial, do you notice a connection between those? That if I do 7 times 6 factorial, that equals 7 factorial. So it's always true that n factorial equals n times n minus factorial. We're just taking the first number in the factorial multiplication and pulling it out separately, and sometimes that makes our work a lot easier. So I just want you to notice that that's true. Okay, then we're going to skip objective 2 and go on down to objective 3, where we're going to use summation notation. And this is just an introduction, but I can guarantee you that it will come up again if you're going to take calculus. We're talking about it in the Calc 1 class I'm working in. We talk about it a lot in Calc 2. So summation notation says, here's k that's called a counter or an index. So its formal name is the index. I call it the counter. It counts from 1 to 2 to 3 and so on. And this number at the top of the summation symbol says when to stop counting. So it says the sum of the a sub k's from k equals 1 to k equals n. So if I write the sum from k equals 1 to n of k cubed, and I say, well, let me let n equal 5. Then that says do 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. So there's a pattern here. So the counter doesn't have to be a k. It can be any number. I, j, k, l, m, n, all of those get used. So let me show you another example. If I let I go from 1 to 4, and I have I to the 5th over the square root of I plus 1. Okay, so the first term says let I be 1. So I have 1 to the 5th over 1 plus 1 in the square root. Then the summation notation says now add the next one. So then I let I equal 2. So I'll have 2 to the 5th over 2 plus 1 inside the square root. Plus 3 to the 5th over 3 plus 1 inside the square root, plus 4 to the 5th over 4 plus 1 inside the square root. So hopefully those examples will help get you the idea of what is the symbol meaning. So we're going to let k equal 0 first in number 50. When k is 0, I get 1 plus. Then when k is 1, I'm going to get 3 plus. When k is 2, I'm going to get 5, and then see the pattern growing. And then plus, dot, 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 the ellipsis that says, and so on in the same way until k gets to the number n, and then you stop. Okay, so we'll look at number 58 in class together with the alternating sign. And then here's some more examples. They didn't have enough examples in your book, I thought, so I gave you some more here. So we'll do this first one and we'll do the next one in class. So you let I equals 3 to start with, so you get 3 squared. Click, now I is 4. 4 squared. Click, now I is 5. 5 squared. Click, now I is 6. Now I is 7, and then stop. Okay, so hopefully that's becoming clear to you. Now the other direction you have to be able to go is to express the sum using summation notation. So first you get the summation notation and write out the sum of what it looks like, but then we have to be able to go back the other way. So I'm going to make another brief movie to do that so that I don't run out of time on this one.